Okay, this is my solution for a big problem that we did about rotation. So this had a lot of different pieces, but that's one of the things I like about this problem actually. This was about disc brakes. And so the idea is that there's a fluid that with pressure pushes a certain little disc against the larger disc of your brake drum. And so by exerting a force on it, you can slow the brake drum down. And so let's say that you're given some initial omega naught. And in the problem, this was given as 1,000 revolutions per minute. And we said that in order to use the rotational kinematic equations, we want to put this instead into radians. And we had to then define what a radian means. And we said that a radian is defined as the ratio between an arc length and a radius. And so if you're given omega in revolutions per minute, what you're really being given is the rate of change of omega, except that in order to convert from revolutions into something that's unitless, you want to convert that as 2 pi radians per revolution. So if it's 1,000 revolutions per minute, it will be 2 pi thousand radians per minute. Okay, having said that though, let's return back to the problem. And let's take as step 1, find the force required to stop the drum in, let's see, and it was given as a time, so in time t. Okay, so let's see. Here we go. Where do we want to begin? Well, a good way to begin is to ask ourselves what the angular acceleration has to be. And so if we use the kinematic equations, we say we can write down that the acceleration is omega final plus omega initial times time. Wait, that doesn't feel right to me. So if these are in units of radians per second, then when I multiply by a t, I would get radians per second squared. No, I get radians. Oh no, that's not right. Okay, let's try this again. So here we go. Omega is equal to omega naught plus alpha times t. That's right. This is sort of like a v equals v naught plus at. And we can always go back and forth from one to the other. So, okay, so we have omega minus omega naught all over t is equal to alpha. Okay, that sounds good. And so if the final speed is 0, then alpha is just minus omega naught over t. Okay, fair enough. So let's see, what's next? Well, what we just did is kinematics. What we need to do next is dynamics. Basically, why do things move the way they do? Not just how they move, that's kinematics, but dynamics. Okay, so let's see. The dynamics is that the torque exerted by the calipers is equal to the moment of inertia of the disk times the alpha of the disk. So this is sort of like an F equals ma kind of equation. However, we do know how to actually calculate torque. And how to calculate the torque is, let's see, to calculate the torque it's R cross F. And in this case, the force is the thing that we're trying to find. And the R here is called the moment arm. and it's given as little r in the picture above. Right here. Okay, so we'll just write it then as r, f. Now, what about the moment of inertia? So we talked about in class that the moment of inertia is the sum of each little piece of mass times the distance that thing is from the center of rotation. If you have a continuous object, it's going to be the integral dm times r squared, where m now may depend on r. But if we do that integral, or we look it up in a table, it turns out to be 1/2 m r squared. This is the moment of inertia for a disk. Okay, times alpha, that thing that we have. So I think we're actually ready to solve for the force. Okay, so we'll turn the page here and do that. And what we find is that, I'll rewrite the one from the previous page because I can't see that now. So this is 1/2 mr squared alpha. So that means the force is equal to mr squared alpha all over 2r. Okay, and we know that the alpha was equal to just, the alpha is equal to the initial velocity divided by time. Okay, you might wonder where the negative sign went. In fact, if I have an object that is spinning this way, the force that is required to stop it actually has to move this way at some distance r from the center. So, okay, this is our answer, I guess, but let's now continue on with how we posed it in class, which is to say, find the pressure in the brake fluid. So to do that, I'm going to remember that pressure is force per unit area. So the pressure in the brake fluid has to be equal to, let's see, has to be equal to the force, mr squared omega naught, all over 2r times the area of the little thing that's pressing on it, times t. So if we plugged in the numbers that we had in class, we had something that looked like this. We had 17 kilograms, and the radius was 0.26 meters squared. The original spinning was, well, let's see. The original spinning was 2 pi times 1,000 radians per minute, which means it has to be 60 times 2 pi times 1,000 radians per second. No, that doesn't make sense. It has to be a smaller number. There we go. Radians per second. And a radian is kind of a fake unit, so that when you multiply it by anything else, like these meters or these kilograms, it goes away. Okay, divided by 2 times where the pistons are against the wheel. So the pistons were 10 centimeters from the axis, so 0.1 meters. The area of them, they had a 2 centimeter diameter, so it's pi times 0.1 meter squared. And let's see, so that's the area, and then the time was, let's see, 5 seconds. Okay, that's the answer, so I'll pause here to plug this all into my calculator. Okay, I'm back, and if I plug this into my calculator correctly, although you should check, I got 3.83 times 10 to the 3. Now let's look at the units. The meters cancel, the meter squared. I have 2 seconds left, so I have seconds squared. I have a meter left, so I have a meter. And then I have a kilogram up top. Well, that makes sense, because a kilogram meter per second squared would be a Newton. So this is a Newton per meter squared. Yeah. So that is 3.83 times 10 to the 3 pascals. And we're done.